Chapter 2 Physics Electrostatic Potential and Capacitance. Introduction. In chapters 5, 7 of class 11, the notion of potential energy was introduced. What is potential energy? We saw in class 11 itself, in both the work energy, power and gravitation chapters. When an external force does work in taking a body from point to another against a force like spring force or gravitational force, the work gets stored as potential energy of the body. When any work is done against a force, then that work will be stored in the body as potential energy. That is why when we release the spring or any object where we kept at a height, the object will fall down or the spring will get compressed, because the potential energy is being converted into kinetic energy. When the external force is removed, the body moves, gaining kinetic energy and losing an equal amount of potential energy. The sum of kinetic and potential energy is thus conserved. Forces of this kind are called conservative forces. We can also define conservative forces as the forces that does not depend on the path as well, and non-conservative forces as something that depends on the path. Here they defined conservative forces as where the sum of kinetic energy and potential energies, when it is conserved, the forces here are called conservative forces. Spring force, gravitational force are examples of conservative forces. Coulomb force between two stationary charges is also conservative force, as here the potential and kinetic energy is indeed conserved. This is not surprising, since both have inverse square dependence on distance and differ mainly in the proportionality constants. The masses in the gravitational law are replaced by charges in the Coulomb's law. If you see, gravitational Fg equals gm1 m2 by r square, whereas F electric depends gq1 q2 by r square. Both are extremely similar formulas, and both forces depend inversely on the square of the distance between them. Thus, like potential energy of a mass in a gravitational field, we can define electrostatic potential energy of a charge in an electrostatic field. As we define when there is an object in the gravitational field or getting attracted by gravity, which we call a gravitational field, where the object is experiencing gravitational force. As such, here as well we can define electrostatic potential energy when a charge is placed in an electric field. This is one of the main topics we are learning here, which is electrostatic potential energy. What is the potential when we take an object from the ground to a few meters high? As the object gains potential energy, a charge as well, when placed in an electrostatic field, it will also gain potential energy. This is what we call electrical potential energy, and voltage is potential difference. Consider an electrostatic field E due to some charge configuration. If there is a charge, when we have a positive charge or any kind of charge, this is what provides electric field. This is what they said in this sentence here, as consider an electrostatic field due to some charge q, charge configuration or some charge we can take. First, for simplicity, consider the field due to charge q placed at the origin. Now imagine that we bring a test charge q from point R to point P against the repulsive forces due to the charge q. With reference to figure 2.1, this one, a test charge q, this charge q has a charge of greater than 0, which means it's a positive charge, is moved from point R, which is far from charge q, to point P, which is near to P, which is near to charge q, against the repulsive force on it by the charge q, which is also a positive charge, placed at the origin. This will happen if q and q are both positive or negative charges, because work is done if they are negative charges. If they are like charges. If they are like charges, they give that bringing the charge R, test charge Q from R to P against the repulsive force. If it is against the repulsive force, then it must be like charges. For definiteness, let us take capital Q, comma Q both greater than 0. Two remarks may be made here. First, we assume that the test charge Q is so small that it does not disturb the original configuration, namely the charge Q at origin, or else we keep charge Q fixed at origin by some unspecified force. Second, in bringing the charge Q from R to P, we apply an external force F external just enough to counter the electric force Fe. That is, F external equals negative Fe. So what they are saying here is, when two charges are repelling, if you take two of these charges, and if this positive charge Q and this charge you are bringing closer, then this charge should be moving away, but they took it that this charge will not move. It may be due to this test charge being so small and so minute compared to this main capital Q charge, that it may not able to move this charge, or this Q charge is fixed by some external force which is unspecified. And the second thing, they assume that this charge is coming from R to P. The work done, if it is coming against the repulsive force, there must be some force applied on this charge Q. That it is an unspecified force, it might be due to any factor, and they took it as equal to the force which is given by which is because of this capital Q charge. That is F external, or the force applied on this test charge to bring it closer to this main charge. That force is, we take it as equal in magnitude to the electric force due to electric field, but it is opposite, so that is why it is a negative sign, where the electric field is acting this side but the force is this side. That is why they took a negative here. This means that there is no net force on or acceleration of the charge Q when it is brought from R to P. That is, it is brought with infinitely slow constant speed. If the forces are equal, the net force is 0. That is what is happening here. The net force is 0. So the acceleration will also be 0, and it is brought from R to P in an extremely small constant speed. When the force is 0, there is no repulsion or attraction, and it is moving there in an infinitely small constant speed. This speed is constant. In this situation, work done by the external force is the negative of the work done by the electric force. So as we saw here, where the external force, the force external is negative to the electric force, the same way the external work done is negative to the work done by the electric force. And when we are bringing this charge, there is a charge plus Q, and there is a point P and a point R. Q naught is a test charge, which is also a positive charge. Let's take it as positive. Q naught, we are bringing it from R to Q naught. Here, this charge is fixed here, fixed by unspecified external force, because when we bring two charges, repulsive charges together, this charge should get displaced in this direction, but that doesn't happen because this charge is fixed in that place. Or another scenario is where this test charge Q naught is very, very minute compared to this capital Q or main charge. But let's just assume that this plus Q is fixed at that position, and we are bringing this Q naught charge from R to P, and there is an electric field. I'm mentioning the electric field here. It will always be there because there is a charge here. We are bringing this Q naught test charge from R to P against this electric field. As there is repulsion between positive charges, we need to apply a force to bring it from R to P in the direction of the capital or main charge. So the force applied, the condition here for the force applied is that we are applying a force on this test charge external. It might be due to any other factors, but let's just call it a force external. This force in NCERT, they took it equal to the magnitude wise, equal to the force due to electric field. The force due to the electric field is acting this side, whereas our force is acting this side. So it will be F external on Q naught test charge will be negative of the force due to electric field. And one more thing they mentioned is when we bring and this is a distance, work done equals force into distance. As such, when we are applying some force F external, and one more point I forgot to mention is when force external is equal to force due to electric field, then there is the net force acting on this will be 0, and as such the particle or the charge, test charge Q naught, will move from R to P with very small and constant speed. And when we are moving this with a force, we are applying a force even though the net force due to the cancellation of the electric force F electric, as we are applying a force and work done is force times distance, there will be a work done. So the work done in moving charge Q naught, the NCERT gave one more point that this is equal to the work done due to the electric field, negative at least. So when we are doing work done, when there is some work done in moving this charge from R to P, this work done or this energy, it is stored. This energy should be stored somewhere, as in this system we do not consider any external forces here. We only consider in our system or our universe there exists only two charges of capital Q, the main charge, and the test charge Q naught. In this scenario, when we move this charge from R to P, the work done for moving that charge should be stored somewhere, as due to conservation of energy, where energy can neither be destroyed nor be created. It can only be transferred or stored from one form to another. Because of that, this energy will be converted into this work done will be converted into potential energy or electrical potential energy, as this potential energy is due to electric field. As we move this charge from here to here, we are doing work, and this work is getting stored as electrical potential energy. Yes, that is the first paragraph. Yes. Yes, let's read the paragraph again. If Q and capital Q and Q are both main charge positive or both negative, for definiteness, let us take capital Q comma Q both greater than 0. Two remarks may be made here. First, we assume that the test charge Q is so small that it does not disturb the original configuration, namely the main charge Q at the origin, or else we keep Q, the main charge Q, fixed at the origin by some unspecified force. Second, in bringing the test charge from R to P, point R to point P, we apply an external force F external, just enough to counter the repulsive force F electric field. That is, F external equals negative of F electric field. This is just a direction because it is opposite. As I showed here, F electric acts in this direction, whereas the force external we apply on the test charge acts in the opposite direction. This means that there is zero net force or there is no net force on or acceleration of the charge Q. There is no acceleration, there is no net force. F equals ma when net force is 0, mass is there, acceleration only in some cases, not all. This is just for understanding sake. So here, as net force is 0, acceleration will also be 0. In such a case, if there is no acceleration, we can assume that the particle is going in a constant speed. When there is force is 0, we can assume that the particle or charge is moving with extremely low speeds. Brought with infinitesimally slow constant speed. In the situation, work done by the external force is the negative of work done by the electric force and gets fully stored in the form of potential energy of the charge Q or the test charge Q. If the external force is removed reaching the P, the electric force will take the charge away from Q. The stored energy, potential energy at P, is used to provide kinetic energy to the charge Q in such a way that the sum of the kinetic and potential energies is conserved. Thus, work done by external forces in moving a charge Q from R to P is work done from R to P, where the lower limit is from point R, where there is less potential, and P, where there is the highest potential, where the basic formula is F times T, and F external is the force we applied to move the test charge, and dr is the distance we moved, which is equal to the negative of the F external between. Yes, because this work done is against electrostatic repulsive force and gets stored as potential energy, that is why it is believed it is negative. At every point in the electric field, a particle with charge Q possesses a certain potential energy. So the before paragraph, We assume the charge, main charge Q, test charge Q naught. When we bring this charge closer from P to R, and this is when, let's assume this is the place we moved we moved the Q naught charge, the test charge, from R to P, and there is still now let's assume at time equals t, Q naught, the test charge, reached point P. Basically I'm saying that we successfully moved Q naught charge from R to P, and this happened at time t equals, let's assume not t but t1. At t equals time equals t1, Q naught reached point P. This is the highest potential point, where PR is the lowest potential point. Now from this configuration, at this time, force on Q naught is F external. Force equals F external. Potential energy equals maximum compared to R, or in this line. Now from this configuration, at the same configuration, at time t equals t2, let's say that force on test charge Q naught, F, I'm not talking about the next net force, but the external force reaches 0. It becomes 0. Then due to the electrostatic force, repulsive force, this Q naught will immediately be displaced far away from the main charge. So we can say this Q naught charge has gained kinetic energy. So this is, as I said before, when the potential when they are close is maximum, and when we released, that potential energy is getting converted into kinetic energy. So this kinetic energy we didn't get from out of nowhere, but we got it directly from the potential energy which was stored when we did that work. How we got that potential energy, if you ask? That potential energy, when we moved the charge from R to P, the work done in moving the charge, which is F times T, that is what gave this charge a potential energy. That potential energy again got converted into kinetic energy just as we released the force. So potential energy got converted into kinetic energy. At every point in an electric field, a particle with charge Q possesses a certain electrostatic potential energy. At any point in an electric field, if we take, that particle will have some amount of potential energy. If we take a charge q and no matter the distance, this is the electric field. No matter how far, if there is a q naught with a distance d, which unless is infinity, d not equal to infinity, but it is not, let's not call it not equal, but it is, let's say d is lesser than infinity, at all points where d is lesser than infinity and there is a charge q, then this q naught charge will always experience a potential. No matter the distance, when it is smaller than infinity, the potential, the electrostatic potential, will always, electrostatic potential not equal to 0 for test charge q naught. Even though it might be very very small, very close to 0, but it will not be 0 at any point at a distance d. But this is not the case for d equals infinity. When d equals infinity, the distance between the charges is infinity, then v equals 0. V is potential difference, or we can just use it as potential as well. But there is another topic, potential energy, that is different. Basically, the basic concept is that things go from high potential to low potential. This is the basic principle. This is almost universal. When we take, this is the earth, there is a ball here, we lifted it and took it here, it has some potential energy, and when we consider at this position or this position, if we consider this is the first position, second position and the third position, the third position will have the highest potential, and second the medium, and first the lowest potential. And due to the gravitational field or gravitational potential, this ball with a high potential will go to the low potential here. By going this way, the potential energy is getting converted to kinetic energy. This is gravitational potential. When we see charges case, and there is a charge here, in the previous chapter we saw that when two charges positive are placed here, electric field this way, this charge will experience a force this side. This is experiencing a force this side. We can also define it in terms of potential. We can say that here there is high potential, as it is from points, let's say A and B. A, there is high potential because the distance between the positive charges is less, and between B there is less potential. Because of that reason, the charge will opt to go from A to B. As to this is also a way of defining why this charge when placed near a positive charge, will experience force. This force is due to the charge being at high potential and going to low potential. At every point in an electric field, a particle with charge q possesses a certain electrostatic potential and energy. This work done increases its potential energy by an amount equal to the potential energy difference between points R and P. Thus, the potential energy difference delta U is U potential energy at P minus potential energy at R, which is equal to the work done. Note that here this displacement is an opposite sense to the electric force and work done by electric field is negative. Let's read that again. Displacement is an opposite sense to the electric force. Displacement is a vector quantity and is opposite to the electric force. Because of that reason, they took the work done to be negative, because distance is not a vector, but displacement, which has a direction, is a vector. And when electric force is acting this way, displacement is acting this way, at least when we go to low potential to high potential against the electric field using some force. The potential difference, how we should calculate? We saw that when positive charge q naught going to main charge q from point R to P, work is done. This, let's call it WRP. This work done is equal to the change in potential energy. Why that is? Because at this point R as well, when the distance between the charges is less than infinity, this will have a potential, this charge will have a potential of UR, and at this point there will be potential UP. So work done from point R, from moving a charge from point R to P, which is equal to potential at UP, which is the high potential, minus UR, low potential, equals delta U, which is the potential difference. So work done equals potential difference. Therefore, we can define electric potential energy difference between 2 points as the work done required by an external force in moving without accelerating charge q from one point to another of an electric field of any arbitrary charge configuration. They say that two important comments may be made at this stage. The right side of equation 2.2, here the WRP depends only on the initial and final positions of the charge. Means that the work done by the electric field in a moving charge from one point to other depends on the initial and final points and is independent of the path taken. No matter if you go semicircle, circle, curve, rhomboid, or whatever it might be, the path, it doesn't matter. Where you were at the initial point, or where the charge is at the initial point, and where the charge is at the final point, that is what determines the potential difference or the work done. Because in this equation we saw that the work done is equal to the potential difference. One point to another. it is independent of the path taken. This is the fundamental characteristics of a conservative force. The concept of potential energy would not be meaningful if the work depended on the path. The path independence of work done by an electrostatic field can be proved using the Coulomb's law. We omit this proof here. They did not give the proof, that's what they're saying. And the second remark, or comment at least, equation 2.2, which is that potential difference equals UP minus UR equals WRB. This equation defines potential energy difference in terms of physically meaningful quantity work. Clearly, potential energy so defined is undetermined to within an additive constant. What this means is that the actual value of potential energy is not physically significant. It is only the difference of potential energy that is significant. We can always add an arbitrary constant alpha to potential energy at every point, since this will not change the potential energy difference. Basically, we are saying that always what matters to us is not the potential energy. When we calculate potential energy, we actually do not calculate actual potential energy of the object itself, as the object's potential energy depends on many factors, but we are actually calculating the potential difference, and only the potential difference. And when we are calculating a potential difference, we don't need to be very accurate, because even we add the any kind of constant alpha on the main potential energy, the final value will be equal to delta U. Because we are not actually doing the potential energy or finding the actual potential energy of this object, we can actually define one of the potential to be zero. If let's assume we have accurate values that potential at point A and potential at point B, we have accurate values. We need to find potential difference. Let's assume at potential at point A the potential is 30 volt, at potential B it is 20 volt. In such a case, the potential difference will be 10 volt. When we only want the main value we want is potential difference. In such a case, what we can do is, we know the potential difference. So we can say that the potential difference across these 2 points, we can, if we don't know we know that the potential difference between points A and B is 10 volt. So at this point the actual potential is 20 volt, but let's assume it is 0 volt. We don't know and we took it as 0 volt. If the potential difference is 0 here, then at point A it will automatically be 10 volt. If we see in these both scenarios where we took that we know the actual values of potential at A and B, which is 30 and 20 volts, and here we do not know and we took B as 0 and A we got due to the potential difference, which is 10 volt, which is the A point is also 10 volts. Because of this, we can take this as 0, but there is no difference here. In these 2 scenarios, the potential difference will be 10 itself. So if we place a charge here, a charge q, depending on the charge it will move on this or this direction at the same like kinetic energy, or we can say, let's just say there is no difference because the potential difference is same. That is why we can take this as 0. That makes us easy for calculations. That makes it easy for our calculations. When we can add a constant, we can also subtract a constant here. To put it differently, there is a freedom in choosing the point where potential energy is 0. A convenient choice is to have electrostatic potential 0 at infinity. With this choice, if we take the point r at infinity, we get the equation V work done from moving from infinity to p equals up minus u infinity, which is equal to up, because the potential at infinity goes 0. Let's use the black pen. 0. Since the point P is arbitrary, equation 2.3 provides us with a definition of potential energy of a charge Q at any point. This is actually infinity. We take it as a really large distance, meaning even though there is some potential at that point, as I said before, the potential is potential is actually truly 0 only when it is complete infinity. But here we can consider it infinity when there is really long distance, or when the charge is really minute. Only when such a case can we take it as the potential being 0. But it's actually not 0, as it will have some value. Potential energy of charge Q at a point in the presence of a field due to any charge configuration is the work done by the external force equal and opposite to the electric field in bringing the charge Q from infinity to that point. The work done in bringing a charge Q from infinity to that point will be the potential energy, or the change in potential energy. Electrostatic potential. Consider any general static charge configuration. We define potential energy of a test charge Q in terms of work done on the charge Q. We define potential energy on a charge Q in terms of work done on the charge Q, as we saw in this equation here. This work done is obviously proportional to Q. As the charge is higher, the work done is higher, based on Coulomb's equation here. F E equals kq1 q2 by r square. Force increases, work done increases, as force depends on q1 q2 or charge, and work done also depends on q. As the charge is higher the repulsion forces, higher the work done. Now, since the force at any point is QE, because we know the equation E equals F by Q and F equals QE, and where is E is the electric field at that point due to a given charge configuration, this we learned in the previous chapter, it is therefore convenient to divide the work by the amount of charge Q, so that the resulting quantity is independent of Q. In other words, work done per unit test charge is characteristics of the electric field associated with the charge configuration. This leads to the idea of electrostatic potential V due to a given charge. We saw that the work done depends on both the charges, but in the electric field as well, the force depends on both the charges. So we define something new here, a new idea, is the electrostatic potential, where we define it only for a single charge. From equation 2.1, which is this equation, where W equals force times distance. Work done by an external force in bringing a unit positive charge from R to P. This is the potential difference, which is equal to UP minus UR by Q, where Vp and Vr are electrostatic potentials at P and R respectively. Note as therefore that is not an actual value of potential, but the potential difference that is physically significant if, as before, we choose the potential to be 0 at infinity. Work done by an external force in bringing unit positive charge from infinity to a point will be equal to electrostatic potential V at that point. In other words, the electrostatic potential V at any point in the region with electrostatic field is the work done in bringing a unit positive charge without acceleration from infinity to that point. Here they gave a figure, work done on a test charge Q by the electrostatic field due to any given charge configuration is independent of the path and depends only on its initial and final positions. This is what we read before. The qualifying remarks made earlier regarding potential energy also apply to the definition of potential. To obtain the work done per unit test charge, we should take an infinitesimal test charge delta Q, obtain the work done delta W in bringing it from infinity to the point, and determine the ratio delta W by delta Q. Also, the external force at every point of the path is to be equal and opposite to the electrostatic force on the test charge at the point. Let's read that again. Let's read the paragraph again. Electrostatic potential, consider any general static charge configuration. Any general static charge configuration, meaning a charge fixed at a point. It might be a positive or a negative charge. Just let's take it as a charge Q, where we saw in the before cases where the main charge capital Q, that is a static charge configuration. We define potential energy of a test charge Q in terms of work done on charge Q. As the work done increases, the potential energy increases. The work done is converted into or stored as potential energy. Because of that, the potential change or the change in potential energy, we define it as the work done on the charge Q from due to the movement or displacement of the charge Q. This work is obviously proportional to Q. As the Q is higher, the repulsive force is higher, the force is higher, the work done is higher, and work done is directly proportional to charge. Since the force at any point is QE, where E is the electric field at the point due to given charge configuration, it is therefore convenient to divide the work by the amount of charge Q. It is therefore convenient to divide the work by the amount of charge Q. So then the resulting quantity is independent of Q. In other words, work done per unit test charge is a characteristic of electric field associated with the configuration. Basically they are saying or deriving the formula which we know before itself, which is V equals W by Q. So they are, I believe what's going on here is a charge Q and test charge Q naught. As we bring this close, or as we bring this from point B to A, work done from B to A will be equal to the change in potential energy from UA minus UB. So we can see that this potential change in potential energy depends on this charge Q and the charge you are moving Q naught. Because it is depending on both the charges, as the formula we know, work equals force into distance, force electric equals kq1 q2 by r square, where Fe equals is directly proportional to, here as well it is Fe, because here the work done is against the electric force, so it is directly proportional to the charges q1 and q2. Because of that reason, work done, which is proportional to Fe, work done is also proportional to q1 q2. In such a case, if you want to calculate the change in potential energy, we should know both the charges Q naught and the capital main charge capital Q, because they consider this as inconvenient and they want to find the potential due to a charge. We are not finding the potential energy right here. This is a difference in potential energy. We are not finding potential, and whatever we are going to do next is not potential energy but potential, V, voltage. This potential is, as it is more convenient if we take it as only the positive Q charge or the main charge, static charge configuration. We saw a similar thing in the previous chapter of the electric field, where electric field of a charge Q, the electric field equals K Q by R square, whereas the force is equals to K Q1 Q2 by R square. The electric field intensity is difference of force by Q, and the electric field due to a single charge we calculated it as KQ by R square. Similarly, the potential here as well, they are calculating based the potential, it's not potential energy but potential, they assuming a single charge. How we can do this dividing? We know that work done is equal to change in potential energy. So based on this, work done is due to two charges, and if we divide this by the Q naught test charge, in our case the charge which we are moving, then we will get potential. This is what they are basically saying. We are completely removing this moving charge by dividing it so that we get the potential. That is basically what I understood. Let's read the paragraph or this electrostatic potential topic again. Consider any general static charge configuration. We define potential energy of a test charge, and as I said before, what we are defining here is not potential energy but potential V. Consider any general static charge configuration. We define potential energy of a test charge Q in terms of work done on the charge Q. This work done is obviously proportional to Q, since the force at any point is QE, where QE is the electric field at the point due to the given charge configuration. It is therefore convenient to divide the work by the amount of charge Q so that the resulting quantity is independent of Q. In other words, work done per unit test charge is characteristics of the electric field associated with the charge configuration. This leads to the idea of electrostatic potential V due to a given charge configuration. Work done by external force in bringing a unit positive charge from point R to P equals change in potential, which is equals to the change in potential energy by Q, where Vp and Vr are the electrostatic potentials at P and R respectively. Note, as before, that it is not the actual value of potential but the potential difference that is physically significant if, as before, we choose the potential to be 0 at infinity. Work done by an external force in bringing a unit positive charge from infinity to point equals electrostatic potential V at that point. In this equation, if we take UR at the point R is a point at infinity, then the potential energy at infinity equals 0, and we can define potential as U by Q. So the potential is the work done by an external force in bringing a unit positive charge from infinity to a point is equal to the electrostatic potential. They took a unit charge. They specifically mentioned a unit charge here, unit. That is specifically because they took this value as 1. When they take it as 1, V equals U equals W. I did not take the delta W here because here this will be equated to 0. In such a case, V equals U equals W, and we can define the potential without defining the test charge. In such a case, the potential will be we can define voltage or potential as the work done in bringing a unit, let me repeat, a unit positive charge from infinity to a point. We can also mention that it is against an electric field or electric force, is what we call as electric potential. In other words, the electrostatic potential at any point in any region with electrostatic field is the work done in bringing a unit positive charge without acceleration from infinity to that point. without acceleration because net force is 0, so it will be brought without acceleration and with very small speed. The qualifying remarks made earlier regarding potential energy also apply to the definition of potential. To obtain the work done per unit test charge, we should take an infinitesimal test charge delta Q, obtain the work done delta W in bringing it from infinity to point, and determine the ratio delta W by delta Q. They are taking a small charge. Also, the external force at every point of the path is to be equal and opposite to the electrostatic force on the test charge. This is the point we saw in the potential energy in the first case itself, where F external equals negative of the F electric. Now, the next main topic, potential due to a point charge. Consider a point charge Q at the origin. For definiteness, take Q to be positive. We wish to determine the potential at any point P with position vector R from the origin. For that, we must calculate the work done in bringing a unit positive test charge from infinity to point P, for where the main charge Q is greater than 0. The work done against the repulsive force on the test charge is positive. Since work done is independent of the path, we choose a convenient path along the radial direction from infinity to that point. At some intermediate P on the path, the electrostatic force on a unit positive charge is Q times 4 pi epsilon naught R square times R vector. Let's read the paragraph again. Consider a point charge Q at the origin. For definiteness, take Q to be positive. We wish to determine the potential at any point with position vector R from the origin. For that, we must calculate the work done in bringing a unit positive charge or test charge from infinity to point P. For Q greater than 0, the work done against the repulsive force on the test charge is positive. The work done against the repulsive force on the test charge is positive. Since work done is independent of path, we choose a convenient path along the radial direction from infinity to the point P. At some intermediate point P dash on the path, the electrostatic force on unit positive charge is Q times 1 by, where 1 is the unit test charge, unit positive test charge, where we took value directly as 1, by 4 pi epsilon naught R dash square, and the vector is R dash vector, where it is some intermediate distance which is not at infinity but at some point between P and infinity. We took it as P dash. At that point, the electrostatic force on a unit positive charge is Q by 4 pi epsilon naught R dash square, where the distance is R dash, times R vector, where R is the unit vector along the OP dash path, where work done against this force from R dash to R dash plus delta R dash Let's see the diagram first. Figure 2.3, work done in bringing a unit positive test charge from infinity to point P. Work done in bringing a unit positive charge from infinity to point P against the repulsive forces of charge Q, where Q is greater than 0, the potential at P due to the charge Q, where this distance is what they took as delta R dash, and here to here they took it as R dash, here to here R dash, no, here to here it is R dash, here it is delta R dash, and from here to here, from Q to P, it is R, where R cap is the unit vector along OP dash. Work done against this force from R dash to R dash plus delta R dash. What we are calculating here is work done, or the change in work done. The negative sign appears because delta R dash is smaller than 0, because we are moving from here to here and the distance, overall distance, is reducing. So from the initial point to final point, initial point where the position was R dash, it became, instead of R dash plus delta R dash, it should become delta R dash. Work done is positive. Total work done by the external force is obtained by integrating equation 2.6, this equation, from R dash, from infinity to R dash equals R, where R dash is the distance between the test charge and the main charge. So integrate it. So we can take out integrate, where these are constants, so take them outside. So the final answer will be Q by 4 pi epsilon naught R. This is the potential. This is also equal to potential. What we are finding is basically the potential. This by definition is the potential at P due to the charge Q. V equals Q by 4 pi epsilon naught R. Equation 2.8, meaning this one, where V equals KQ by R, you can write it, I can take 1 by 4 pi epsilon naught equals K, so V equals KQ by R, or 1 by 4 epsilon naught q by r, like here, is true, that equation is true for any sign of the charge q. The charge may be a positive charge, negative charge, it may be of charge of any magnitude. It is true for any charge q. Though we considered q to be positive in its derivation, for q greater than 0, lesser than 0, potential is lesser than 0. That is, work done by external force per unit positive test charge in bringing it from infinity to the point is negative. That means this scenario happens when it is attraction force. How work done can be negative is when we take a negative charge here q and positive charge q naught, there is a attraction force. Due to this, in this case, let's assume this is the point A and this is the point B. In such a case, point A will have higher potential. In other words, A, B, we know that any kind of particle or anything moves from high potential to low potential. Because of that, the charge q naught without any external force will move from A to B, and because of the attraction forces, and due to this high potential energy, this potential energy gradually gets, as is moves from A to B, the gradually gets converted from potential energy to kinetic energy. The work done will be negative. This is equivalent to saying that work done by the electrostatic force in bringing the unit positive charge from infinity to point P is positive. This is as it should be for q smaller than 0. The force on a unit positive test charge is attractive, so that the electrostatic force and the displacement from infinity to P are in the same direction. Finally, we arrive at the note that equation 2.8 is consistent. 2.8, V equals kq by r, or V equals 1 by 4 epsilon naught q by r, is consistent with the choice that potential energy at infinity B is 0. This figure, variation of potential energy V with r in units of q by 4 epsilon naught per meter, blue curve, and the field with r in units of q by 4 epsilon naught or per meter square, black curve for point charge q, capital Q, as this, the blue curve is the potential where the potential, as the radius increases, this is the highest point where the radius is very less. As the radius keeps on increasing, as this reached 1, drastic decrease. As this keeps on increasing, this is for the electric field. As this keeps on increasing, the distance keeps on increasing, this keeps on decreasing. This is because depends on E is inversely proportional to 1 by r square, and as the distance increases, it continuously reaches close to 0. And in case of voltage, here voltage is inversely proportional to 1 by r, whereas here it is 1 by r square. Because it depends on 1 by r, the decrease is, even though it is exponential or it is high, the decrease as we see at this point, it is maximum when it is less than here at this point. As the radius keeps on increasing or the distance keeps on increasing, it keeps on decreasing as well. But it is this distance, or why the potential is not decreasing as drastically as electric field, is because electric field is inversely proportional to r square, where V is inversely proportional to R. Figure 2.4 shows how the electrostatic potential and the electrostatic field varies. Basic problem using the formula 2.8, which is V equals KQ by R, but we should convert this 9 centimeter into meter because that is a SI unit. This one, obtain the work done and bring a charge 2 into 10 power minus 9 coulomb from infinity to the point P. Where this is the Q main charge, and bringing a charge 2 into 10 power minus 9 from infinity to that point, that is the potential itself. Does the answer depend on the path along with which the charge is brought? No, it does not depend on the path, as we know that potential is conservative. Directly applying the formula, we get the answer, which is equal to 4 into 10 power 4 volt, where here we use the formula V equals QV, where Q is the charge we are moving, times the potential, where we are bringing it from infinity to that point. But if that is not the case and we are bringing it not from infinity but from another potential, then the work done equals Q times V at the final point minus V at the initial point. This is the formula, where V at the initial point in case of infinity, where Vi will become V infinity, this will become 0, so we can directly substitute V equals QV, but here it is QV. But in other cases where the distance is not infinity, we use this formula. no work done will be no. There it does not depend on the path. Work done will be path independent. Any arbitrary infinitesimal path can be resolved into two perpendicular displacement, one along r and another perpendicular to r. The work done corresponding to the latter will be 0.